You'll find that this particular test is very similar to the one from section 11.1, where we had two groups, population 1 and population 2. And the way this is going to work is we're going to take a sample from the first group, and we'll take a sample from the second group. And the data we're collecting in this case is numerical data. Back in section 11.1, it was categorical data. Qualitative. Yes, no. Did you eat? Do you eat the recommended number of daily servings of vegetables? Yes or no? What was the other one? Oh, did you earn a college degree? Yes or no? So it's just they earned a college degree or they didn't. It's categorical. In this case, in section 11.3, we're going to do hypothesis testing about two population means, but now they're from independent samples. In section 11.2, they were from dependent samples. We call that matched pairs or before or after. Now, these data values come from two different populations. They will be independent of one another. The information that we're going to be taking out of sample 1 is the sample mean of the first group, the sample standard deviation of the first group, and the sample size of the first group. So we're not taking X and N and then calculating a p hat. We're going to be using numerical data, so we summarize that with a mean. Similarly, down in the second group, we're going to take a mean of the second group. We'll also report the standard deviation and the sample size of the second group. And then we're going to compare these two means, these sample means. And then based on their difference, we're also going to use the standard deviations. Based on these summary stats, we're going to say, is there a difference between the first population mean and the second population mean? So you can see that the test statistic in this case is a t. Now so this is going to be a t distribution, but the degrees of freedom in this test is determined by this very complicated formula. And in many cases, it's, well, in almost all cases, it's not even going to be a whole number. So we're not going to be able to go to our t table and figure out what the critical values are, because this assumes that we have a degrees of freedom that is equal to a whole number. So we'll only be using the p-value approach on this particular test. If you wanted to estimate the degrees of freedom, it's approximately equal to n1 plus n2 minus 2. You could estimate it that way. All right, now, theoretically, if there's a big difference between these sample means, then there would be a big difference between the population means. Population mean 1, mu 1. Population mean 2, mu 2. So we use the Greek letters for the population parameters, population means in this case, and we use X bars to represent the sample means. Okay, hypotheses. What you'll notice for the two-tailed test, left-tailed test, and the right-tailed test, in every case, the null hypothesis is the same. This was similar to what we did in section 11.2, where the null hypothesis was always P1 equals P2. In this case, we're going to assume no difference between the two population means. And if there's no difference, the two are equal. So we're going to claim that these two are equal, and then our sample statistics will let us know if there's evidence to support that the two population means are equal or they're not. Also, as before, notice we have the same two variables in each case. The two-tailed test, we have the not equal to sign. The left-tailed test, we have the less than sign. It's consistent with what we've done in the past. And the right-tailed test, we have the greater than sign, also consistent. So there's the hypotheses, identifying the level of significance, no change there. Usually it's going to be given in the problem. All right, so here's some notes. They give you the test statistic here, the formula, but what we're going to use is the 2 sample t-test. And this is our new calculator function from this section. Now you can, since this will be numerical data for which we can calculate a mean, you can enter these numerical data values into 2 different lists. So for example, you can put the data from the first sample, from the first population into L1, and you can take the list of all the data from the second population and put it into L2. Or sometimes the problems will just give you the summary statistics, X bar, SX, and N for the 2 populations. Step 4 and step 5 are the same. If P is less than alpha, reject the null hypothesis. And then down here tells you how you would, what you need to do with your calculator to enter in the summary statistics or the data. And there's a confidence interval over here instead of the 2 sample t-test, it's 2 sample t-int. All right, what I'd like to do now, that's kind of an overview of differences in the steps. I now want to take a look at a couple of problems that are on this worksheet. And the first one deals with walking in the airport. So you have 2 populations. Do people walk faster in the airport when they're departing, getting on a plane, or when they're arriving, getting off the plane? And so researcher Seth Young measured the walking speed of travelers. I don't know how he did this. Maybe figured out how many distance, how much distance they traveled in, say, 10 feet. And he just was sitting there with a stopwatch, calculated the speed at that point. This was at the Cleveland International Airport. Okay, so those that are arriving, looks like you calculated in feet per minute, and then the standard deviation, and then the sample size. So this is departing. Depends on whether they're late for their plane. And then they take a sample, and we have X1, S1, and N1. This table is just kind of putting all that in a summary. So the mean would be 260, standard deviation 53, and then the sample size was 35. And then for those arriving, he took a random sample of the arrivals. This is X bar. X2 bar was equal to 269. Doesn't look like a big difference between the two. 9 feet per minute. That's not that big of a change. S2 is 34, and N2 is 35. We do observe a difference. This one's 9 more than this. So our question as statisticians is this difference that we observe, is it statistically significant? You can also ask the question, is it practically significant? Is one really going faster than the other if one covers 9 feet more in a minute faster than the other group? So 9 feet in a minute is not a very faster pace, I should say. Okay, let's go through the 5 steps. Step number 1, hypotheses. And in this particular test, we're trying to say something about mu1 and mu2. And the null hypothesis is always a statement that there is no difference. In this case, there's no difference in the speed of walkers. No difference. And I guess I have to read the problem. Do people walk faster in the airport when they are departing, getting on a plane, or when they are arriving? Well, it doesn't look like they want to, commit to one or the other. So they're saying one or the other. So we're just going to say that if one is larger than the other, we don't know which direction it's going to go. So we're just going to say not equal to. This would be that on average, they walk at the same pace, the departers and the arrivers. And this one says that they're different in some way. And then this one says, do they walk faster? And they're not going to commit to either of the two groups, but I think they're saying that one will definitely walk faster than the other. They just don't know which one is which. All right, now these are two variables we use in our hypotheses, so we must define them both. And since they are population means, you can start off with the word mean or the word population. What you can't say is a sample mean, because these are not sample means. The mean walking speed of, I'll just call them departers at the airport. And then mu2 would be the mean walking speed. And remember, that's in feet per minute of arrivers at the airport. All right, here's an example. As we go to step 2, I don't see the alpha. It may have been in the other problems that I didn't copy here, but I don't see it. So I'm going to say alpha is equal to 0.05, which is usually what we would establish as alpha if one is not given in the problem. So there's going to be no classical approach for this one. So I'm going to go right to the 2 sample t-test. 2 sample t-test. All right, now when you go there, we have the summary stats. We don't actually have the raw data that, that Mr. Young collected here. We don't have a list of all the data values we can put in L1 and L2. We just have the summary stats for each group. So you're going to have to enter in all of these. And so as before, the input will be the summary stats. If you selected the data option this time, you'd have to enter in data for the first group in L1 and for the second group in L2. And you're actually going to have the first list and the second list if you select data. But we have summary stats. There's no need for a null hypothesis row here because in this particular test, the null hypothesis is always that mu1 is equal to mu2. So they're going to go right to x1 bar, s1, and n1, x2 bar, s2, and n2. So you're going to have to enter in all 8 of these values here. And then after that, there's this option down at the bottom that says pooled. Well, there's 2 ways you can do this test. One where the variances are pooled and another one where they're not pooled. The one where they are pooled is one where we need to know something about the population variances or standard deviations, and we don't. And so we're safe if we just select always the no option here. The variances are not pooled. And then the final thing is mu1, something about the alternative hypothesis. And our hypothesis is not equal to, so that last row there, you want to select the not equal to mu2 option. All right, so let me fill in the rest of these numbers. I'm just bringing them down. Over there. And as before, this is going to give us a test statistic. and a p-value. Right. And it would look like this. All right, so 2 sample, t-test right there. Option number 4. All right, now if you do have the raw data, then you'd select data, and you could put list 1 as L1, list 2 as some other list, and then you'd have ones for both of these. All right, and then pooled no. So for our tests, we're going to say always no. All right, instead we're going to select the summary statistics, and then we're going to put in all these numbers. 260, 53, and 35, 269, 34, and 35. Not equal to, pooled equals no, and then we calculate to get our test statistic and p-value. All right, so they start off by telling us that our alternative hypothesis is mu1 not equal to mu2. There. And then it gives us the test statistic and the p-value. See what I mean about degrees of freedom being a decimal number? But if you take n1 plus n2 and subtract 2, what do you get? Well, you get 35 plus 35 minus 2, and 70 minus 2, 68. Now you can see it's not quite right. So they give you the, they report back your summary statistics because it's just easier that way. They wouldn't have to write 2 tests. They could just make this always report out these summary statistics. We entered them in, so we really don't need these numbers, but if you had all your data entered into L1 and L2, then you would definitely want to write down those numbers. Okay, less than a standard deviation below the mean, negative 0.84, I'll just call it 6 if we round it to 3 decimal places, and our p-value is 0.401. All right, if we compare P and alpha together, P is 0.01, alpha is 0.05, and we have a greater than. So P is greater than alpha, so we do not reject the null hypothesis. All right, so if we do not reject, then we do not show support for the alternative. Well, the claim was the alternative, so we don't have enough evidence to support the claim. And that's what we're going to write up here. We saw this difference in walking speed, but the difference that we observed is not statistically significant. So this difference could have been caused by just random sampling variation. We just happened to select some faster walkers, arrivers, than departers on that particular day, is what we're going to say. All right, there is not enough evidence to support the claim that. All right, and then we just go and put this claim into words. So what is this? This is the rate of the departers and the rate of the arrivers. They're not the same. There is no difference, or there is a difference between the walking speeds of again, use your own words here. I'll just call it the departers and arrivers at the airport. Now, to contrast this one, where all the summary statistics were given to you in a nice little table like this, and you can compare here, and this next problem, they don't give us the summary statistics, but rather they give us some raw data. And so they took a cubic foot, yeah, I have to think about this in terms of a carpet, but so they went and measured the bacteria in carpeted rooms versus bacteria in uncarpeted rooms. And they counted the bacteria in these rooms. Here you can see that we have N1 equals 8 different rooms. And they had 11.8, on average, 11.8 bacteria per cubic foot. And the same thing over here. N2 is equal to 8. But we don't know what the averages and standard deviations are here. And the claim is, do carpeted rooms have more bacteria than uncarpeted rooms? Here's the carpeted room data. Here's the uncarpeted room. Now, maybe these researchers, this is hospital carpeting here, so maybe these researchers think, you know, we don't want carpet around here because carpet just holds all these, you know, bugs and bacteria and various other things. So they actually did a study to find out, is there in fact more bacteria in carpeted rooms than in uncarpeted rooms? So, and let's see, to determine the amount of bacteria in a room, researchers pump the air from the room over a petri dish at the rate of 1 cubic foot per minute for 8 carpeted rooms and 8 uncarpeted rooms. Colonies of bacteria were allowed to form in the 16 petri dishes. Results are presented in the table. Okay, now we know how they've done it. The data are approximately normal with no outliers. This is one of the assumptions of this test. And then, do carpeted rooms have more bacteria than uncarpeted rooms? All right, so we're going to start off with the hypotheses. Same. And now they say, do carpeted rooms have more bacteria? So here they're making a commitment to more. So carpeted rooms have more than uncarpeted rooms. Now, I can either put the greater than sign here or the less than sign. I would put the greater than sign, which is what I'm going to use, if the first group is the carpeted rooms group, because then it says the carpeted rooms have more bacteria, greater than the number of bacteria on average than the uncarpeted rooms. Now, if I called the uncarpeted rooms the first group, then my sign would be just the opposite. It would be less than. All right, so it's only this if I call the mean, mu1, the mean bacteria in the carpeted rooms. And this is going to be my claim. And mu2 would be the mean bacteria in the uncarpeted rooms. So there's step 1. Here's step 2. We've got the alpha equal to 0.05. And now we have to find x1 bar, s1, and n1, and all of these. But we don't have the summary stats given to us anywhere in the problem. So what we're going to do is we're going to select the data option. So the first thing you need to do is to enter in to your data list, clear those out, and enter in L1, the data for the carpeted rooms, and in L2, the data for the uncarpeted rooms. There's only 8 apiece. It's not going to take that long. Type these in. Now, there's no requirement here that the sample sizes have to be the same for the two rooms. You know, we could have 10 uncarpeted rooms if we wanted. It just so works out that that's how they conducted this test. All right, so I can see I already have an error, 13.7 there. You should probably make sure that you don't have any obvious errors in the data. You could do one variable statistics for the first group and get a mean of 11.2 and a standard deviation of 2.677. And then do it again for the second list. Looks like it's a little smaller here. 9.7875 and S2 equals 3.210. Now this is an optional step because when you run the two sample t-test, it'll actually calculate the mean and the standard deviation and the sample size of both groups together. So I want to show you how that happens. So we're going to run the two sample t-test. And for this time, the input is going to be data. You need, I think they call it list 1, L1, list 2, L2. This is what it looks like. Two sample t-tests, command number 4. I'm going to select data. And then my list 1 is L1. And my list 2 is L2. So I have to change this L3 to an L2. It's currently in the alphanumerics mode, but all I have to do is hit the second key and then the number 2. Second turns the cursor from the A to the shift, and then 2. Frequencies will be 1, and then I think our alternative was greater than. We mentioned that pooled will always be no, and then calculate. And as always, alternative hypothesis, mu1 greater than mu2, right there. It gives you the test statistic and the p-value, but notice what comes next. The mean of the first group and the mean of the second group. So it calculates those for you. If you go down further, it gives you the standard deviations, and it also gives you the sample sizes. The information we need from this output is the test statistic t and the p-value. If you take n1 minus n2, 16, and subtract 2, you get 14. Pretty close to 13.56. Okay. Our test statistic from the output is t, which is 0.95, I'll round it, so 956. And then the p-value from the calculator output is the p, second thing that's printed out, 0.17. Again, if I round it to 3 decimal places, 0.178. All right, the p-value, 0.178. The alpha value is 0.05. And the 178 is definitely larger than the 0.05, so p is greater than alpha. And that always means do not reject the null hypothesis. All right, so since we can't reject the null hypothesis, we can't show support for the claim. So that's how we'll write it up. And the claim is that carpeted rooms have more bacteria than non-carpeted rooms. Didn't appear to be the case this time. I guess they keep those hospitals pretty clean no matter what they have on the flooring. All right. The conclusion, there is insufficient, not enough evidence at the 0.05 level to support the claim that on average, carpeted rooms contain more bacteria than non-carpeted. And those would be hospital rooms.